Good evening, everyone, and thank you for joining us again for the University of California Observatories Living Room Lectures. This evening is the first time that I've actually been in my living room during this presentation because my adorable but very, very loud toddler is actually out of the house. Dr. Ryan Foley is joining us from his gorgeous home office. He's an assistant professor at the University of California, Santa Cruz in astrophysics and astronomy. Dr. Foley studies exploding stars, often with a telescope from the top of a mountain. He's interested in characterizing the many ways that a star can die. He received his PhD from UC Berkeley in 2008, was a Clay Fellow at the Harvard Smithsonian Center for Astrophysics, and is now a member of the UC Santa Cruz faculty. As many of you know, he's also a Sloan Fellow, a Packard Fellow, and a Cobley Fellow. He was awarded a 2018 Nexties Award in the wildcard category, and his team's discovery of first light from a gravitational wave source was named the 2017 Science Breakthrough of the Year. He's close to the beach, so jealous, and tries to see the ocean every day. I believe he's here in Santa Cruz with me. Thank you so much again, Dr. Foley, for joining us.
Well, thank you all. Thank you, Natasha and Marianne. Thank you all for joining in, especially this time of day. Good to see those of you that have your video on. By all means, hi. By all means, feel free to turn on your camera if you want to share in the community a little more. And there's also a chat option on Zoom. By all means, also, at any point during this presentation, put a question into the chat. I might not get to it immediately, but we're going to have some time at the end of everything where I'll be able to go over things. And sometimes, you have that question in right at that moment, and then you forget about it 10 minutes later. At least I have that problem. So feel free to just throw things in there as we go along, and then we'll catch up at the end. Okay, so with that, I'm gonna try sharing my screen. This is always an adventure in this virtual view that we have. Okay, so hopefully everything is sharing okay. And so I wanted to talk a little bit today about, as the title says, Einstein, Hubble, dark energy, and the next breakthrough. Obviously, there are some pretty famous names there at the start, Einstein and Hubble. Dark energy, maybe some of you have heard about. We'll get into it a little bit in a bit. And then the next breakthrough, part of the reason I'm talking about this is my aspirational view of things, that I think that there could be a really important science coming up in this area in the next few years. And part of it is also that there was this previous breakthrough that maybe some of you have heard of. So just to start off with, I always like to point out the team working here in UC Santa Cruz. So this is me and at least some of the team members. We actually have a very large team of mostly students that are working with us. UC Santa Cruz is absolutely fantastic, has amazing students. And I'm really proud of everybody who's here. One of the things I'm most proud of is the diversity of our team and just how young we all are. Our team is majority minority, and so we are trying very hard. We're not quite there, but we're working towards the goal of having the population of astronomy in general at UC Santa Cruz, and in my team in particular, reflect the population of California. So this is a nice start. And really, these are fantastic people that have been able to do some amazing work. And so some of you may know me because of this discovery from a few years ago now, where we detected gravitational waves from merging neutron stars. And then our team went in and saw the light associated with it. This is that first image on the left there, and then an image a few days later on the right of this kilonova that we were the team that found the first photon, the first optical photons from this source. And so this was in 2017 considered the breakthrough of the year. So this is why we're going to have hopefully another breakthrough soon, because I'm not going to be talking about neutron stars today. Some of you have already heard me talk about those. Instead, I'm going to talk about a field that's a little more mature, one of cosmology. And this gets back to work that I started when I was a graduate student. So this was me a while ago when I was younger and had shorter hair, working with my PhD advisor, Alex Filipinko, who many of you will also know. Here we are in the Keck control room where I spent dozens of nights during my graduate experience, and I'm very fortunate to be able to continue to use as a faculty member at UC Santa Cruz. And so a lot of this I've worked very closely with Alex on this work, and Alex, of course, being a little bit older than me, was significantly involved in the discovery of dark energy. And so, it's really been great to be part of that family. So before we dive into the cosmology, I wanted to start off with something a little more basic, and that's just gravity. So if we remember the initial thought of universal gravity that Isaac Newton came up with, there was this fable of the apple falling from the tree. And the basic idea here is, as the apple fell, Newton realized that what happened was that the apple always was being pulled down to earth by gravity, and that gravity is actually not just that the earth is pulling down on the apple, but that the apple is also pulling up on the earth, and that anything with mass is pulling on everything else in the universe. And exactly how that force works out is that it's proportional to each of those masses and inversely proportional to the square of the distance between those masses. So things that are closer together makes the force stronger. If they're further away, it's weaker. If they're more massive, it's stronger. And this is universal in the sense that it works on the surface of the Earth. It works throughout the universe. And so another common way of thinking about this is that the moon going around the Earth is also caused by gravity. That the Earth is pulling on the moon, which makes it so it doesn't fly off into space. But at the same time, the moon is pulling on the Earth. And we know this, especially in Santa Cruz, very well by seeing the tides. So that's a very, very clear source of gravity from the moon. Now, this image here is a little bit of a lie, because it looks like the moon is just going around the Earth. But the reality is that they're both going around a central spot in the sky that's the center of mass of the entire system. And if I show a very similar view, this is Pluto and its moon Charon. And because those two objects are very similar in mass, what happens is that the center of mass for the entire system is not inside of Pluto, it's outside of Pluto. And so it's got this dance between the two of them. And the same thing happens with the Earth and the moon. It's just a little subtler because the Earth is much more massive than the moon. So now that we've got an idea of how gravity works both on Earth and in the universe, now we can think a little bit about how gravity works on moving objects. So it's baseball season again, or at least for the moment. Maybe tomorrow it'll be a little different. But hopefully we can all think about throwing a baseball up in the air and what's happening there. So if we toss the ball up in the air, then what happens is, it will be rising because you threw it up there. But at the same time, gravity is pulling back on it, right? So gravity is always working on that baseball. And so if, you do this, again, and you play the whole thing out, the ball will go all the way up to some apex and then come back down to the Earth. So what that means is sort of an interesting view, because if you had only seen it when it was going up, you might think, well, how is gravity working on that ball, right? It's moving away from the Earth. Well, the way you can tell that gravity is still working on the ball, even when it's going up, is that it's decelerating as it goes up. It's slowing down as it goes further and further up until eventually it stops at this apex, and then it will return back to the Earth. Now that's if you are like me and you can only throw the ball so far. Now, if you were able to have some sort of literal cannon for an arm, you could throw it to the point where you threw the ball hard enough that it could escape the Earth's gravity, in the sense that it will never come back to the surface of the Earth, but it will never escape the gravitational force of the gravity. Gravity will always be pulling back from the Earth, even if it's very, very far away. So all those interstellar space probes that we've gone, Voyager 2 and all these things, that will never come back to Earth. The Earth's gravity is always pulling on it. So this is sort of the basic thing, is that even if something is moving away, you can still detect the force of gravity through the deceleration of that motion. And unless it has some sort of active rocket or something like that, if you just gave it an impulse at the start, like you threw a ball, unless you have some sort of continuous propulsion, then you will always be decelerating. You only have that initial impact, and then gravity, this force, is always going to be pulling back on you. So you can only decelerate from your initial acceleration. Okay, now this works for baseballs. This also works for the universe. So the biggest throw you can ever imagine is the Big Bang, when the universe effectively began. And in this giant, energetic event, we created a bunch of galaxies, eventually, and those galaxies are moving further and further apart from each other. And that is the throw. You're giving this impulse to all these galaxies, and they are moving apart from each other. And when I say they're moving apart, we need to be a little careful about the exact nomenclature here. So normally you think of the Big Bang and you think of an explosion, where it's like a firework or something like that, where stuff just moves away from each other. It's not exactly that for the Big Bang. In fact, what we have is expansion of space itself. That the area between galaxies is expanding over time. The galaxies aren't necessarily, they might move a little bit, but they're not physically moving away from each other throughout space. It's really that the space in between them is expanding. And it can look, from an astronomer's point of view, it can look very, very similar. But we'll get into how you can kind of separate these in a little bit, and what we can figure out about the physics of the cosmos from that. So getting back to our baseball analogy, essentially this Big Bang expansion is this initial throw. The galaxies are expanding away from each other, but the gravity, because all these galaxies have mass, the gravity between the galaxies is pulling back against that expansion, and that should be slowing down the expansion over time. The expansion should be decelerating. Okay. All right, so that's the basic picture. There are no engines in these galaxies. The galaxies should just be, even if they are expanding away, in the same way that you throw the baseball up, even if you throw the baseball far enough where it will never come back down to Earth, you should always be tugging back on that. And this basic idea is extremely successful at understanding how the universe has come to be. So here is this gorgeous, and it takes a little bit, so I'll let it start running, this gorgeous simulation of how galaxies formed in the universe. So it starts off billions of years ago in this sort of initial state of the universe where it was hot and relatively homogeneous. And then over time, gravity is pulling together the densest parts of the universe. And in those dense parts, we're forming galaxies, we're forming stars. You can see this cosmic web where there are filaments between these clusters of galaxies. And at the nodes of all the filaments are where you have galaxy clusters. This continues on for billions of years, and it can reproduce exactly, more or less, what we see when we look out in the sky. We see clusters of galaxies in exactly the same way that the simulations predict. So this is really, gorgeous computer simulations, but essentially we're seeing exactly the same thing. When we look out in the sky, it's just not, it doesn't look as pretty because our telescopes aren't quite this powerful yet. Now, all right, now we have to pause for a second. This is the first part, gravity. Now for the simpler thing, something that we all experience, I'm going to give an example of something called the Doppler shift. All right, you've probably heard this at some point. If you haven't heard this, you've heard the effect for sure. So here's the example of the Doppler shift. All right, everybody listen. Okay, hopefully that was enough for everybody to get the idea. It's that same thing that we've heard over and over again, where a car passing, especially if you hear a siren or something like that, the pitch of that tone changes when that car is approaching and then when it's going away from us. And that change in tone is the Doppler effect. And we hear it very clearly in sound waves, but it also happens with light. So what's really happening is whenever you have something that's moving towards you, it compresses the waves, whether it's light waves or sound waves, it compresses them so that it goes to shorter wavelengths or higher frequencies. And then when something is moving away from you, it means that the sound waves or light waves get stretched out so that they go to longer wavelengths or they're going to these lower frequencies. So that's when you hear that, you're going from the higher frequency to the lower frequency. So you can tell by it being a higher pitch that it's coming towards you, and when it's a lower pitch, it's going away from you. And the same thing happens with light, except with light, instead of talking about pitch, we talk about color. So if something appears bluer than it should, that means that it's moving towards us. And if something appears redder than it should, that means that it's moving away from us. Now, when I say when it should, usually what we are talking about are specific wavelengths of light that have to do with atomic transitions. So if you've ever looked at like a neon lamp, what's happening there is that in those lamps, if it's neon in particular, the neon atom, the electrons are being excited by some charge going across the tube, and then when those electrons de-excite, it releases some light at a very specific wavelength of light. And that's why, if you look at some neon lamps where they're neon or argon or helium or things, they have different colors because that's a fingerprint for each of those elements. Now, that's a little bit advanced, but the basic idea is that fingerprint for each element is very specific. And all of those individual transitions, all those wavelengths, it's shifted by the same amount if something is moving towards you or away from you in this Doppler shift. And so when this happens, you can determine exactly by measuring that shift in wavelength, that shift in frequency, you can measure how quickly something is moving towards you or away from you. So this is the way, by listening to that tone, you could have told me exactly how fast those cars were moving. And by looking at the light from a distant galaxy, you can tell me how fast that galaxy is moving towards us or away from us. All right. Now, this is what Edwin Hubble was able to do, almost 100 years ago now. He looked at galaxies and was able to determine their distance and determine how quickly they were moving towards or away from us. And when he compared the two, here I'm showing his original graph of this, where he's showing the velocity as measured from the redshift and the distance, which he is able to determine independently from variable stars. He looked at a bunch of different galaxies, and you can see that there is a relationship here, where the further away you go.
Are you planning to cook tonight?
Yes.
Sorry. So the further away you go, I believe I can even show. All right, good. So the further away you go here, the higher the velocity, the bigger the redshift. And the closer, the smaller the redshift. And in fact, some are even blue shifted. And this relationship means that on average, not only are galaxies moving away from us, the Milky Way, but the further away they're moving, the faster they're moving. And so either that means we are extremely, extremely special, where somehow we are the center of the universe. And I know maybe some of you do believe that you are the center of the universe, but I'm here to tell you that you are not. And neither is the Milky Way. In fact, what this is it's showing that the universe itself is expanding, that space is expanding, that every galaxy is moving away from every other galaxy. And a really nice analogy is to think about rising raisin bread. And maybe some of you in your quarantine have gotten really into making bread. Maybe you've even made yourself some raisin bread. But this is the basic idea: is you have this clump of dough, and raisins are spread all around. Think of the raisins as being galaxies, and the bread as being the space between galaxies. Now, as we watch the raisin bread rise, what ends up happening is that all of the raisins are moving away from each other. That when the bread rises, there's no, I mean, there is a center here, but there's no one raisin that is kind of stationary. All of the raisins are moving away from each other. And so just schematically, this is the way to think about it: is as that bread rises, the raisins that are towards the outer regions are going to move a little bit further. These are going to move a little bit further away than the ones that are closer to this central raisin. And if you were instead on this raisin, what you would see is that the ones closer here are not moving as far away as the ones that are much further away. So for every raisin in this loaf, all the other raisins are moving further and further away from each other. And the same thing happens with the Milky Way or the sun and other very distant galaxies. Everything is moving away from us. So this is a way that we can determine then the expansion of the universe today by looking at how quickly the galaxies are moving away from us. Tells us something about how fast that the universe is expanding. We know it's expanding, they're moving further away from us. So that's like saying that the baseball is still going up in the air. Now, gravity should be pulling back on it, right? So gravity should be pulling down. So you should be decelerating, but you can still be expanding. Now, another way to think about this is in terms of what we call the scale factor of the universe. So the scale factor of the universe is telling you how large the universe is. So how far apart galaxies are on average. And we know that the universe used to be smaller. So that scale factor was smaller earlier on in time. So if we think about the scale factor as a function of time, because we know that the universe is expanding, that scale factor has to be increasing with time, at least right now. And when we think about what's called the Hubble Constant, that expansion rate, what we're doing is we're measuring the slope of this expansion right at this time now. And if we had no mass in the universe, if we had no galaxies or anything like that, if we had what's called an empty universe, then we would just expand in this linear way, right? If you threw a ball and there was no Earth, it would just keep going. There'd be no deceleration. Now, if we add a little bit of mass to the universe, then you have this slight deceleration. Now, this is like if you're on an asteroid, if you're like the Little Prince and you throw a baseball, the gravity from that asteroid is going to be so small that you can really throw it away and it'll just the baseball will keep going forever. But that asteroid will pull back on it. There is some gravity there. Now that affects what happens in the future, but it also affects what happened in the past, right? So the expansion rate was different in the past for these two different scenarios. And you can just keep adding mass. So if you have a little bit more mass, then the expansion is a little bit different. Now notice again, all of them have the same slope today. That's because we know the current expansion rate. So they all have to match up there. Now, if you overloaded the universe, if it were big enough, if there were enough mass, then this is like, you throw the baseball, eventually it's going to turn around and come back down. So in this case, if eventually the universe could stop expanding and turn around and start contracting to the point where eventually the scale factor would be 0. Everything in the universe would be on top of itself, and that's called the Big Crunch. It's the opposite of the Big Bang. Now, these are all very reasonable things to think about, and this was in fact what we thought for decades the universe was like. But there is an alternative, and some people thought about this in theory for a while, that maybe you don't just have this gravity pulling back. What if you had some sort of cosmic anti-gravity, something that was pushing you as you moved further and further apart? Well, then it would look something like this green line, where the expansion rate would go larger and larger over time, and then earlier on it gets kind of weird, and that's because there's both mass and this anti-gravity. Okay, so this is great. This is great to think about, but we as astronomers want to actually measure something. So what we want to do, if we are thinking about this, is we can only look backwards in time. We can't look forwards in time. So we're looking at that backwards region. Here we are today, so time now, and at redshift of 0, so there's no shift today. If we go back in time to a point where the universe was smaller, where you were going back to this expansion was less, that's saying a redshift of what we call 1, when the universe was roughly half the size of what it is today. Now, what happens is, when you try to measure what that expansion is when the universe was half its size, how long ago was that? Well, these different times at that same expansion rate, at that same size of the universe, that tells you something about the content of the universe, how much matter there is. And so you could say, all right, well, I measured the time it was at redshift 1, and it was here. Well, it means that the universe is eventually going to undergo a big crunch, or it's here, and then we have a very soft expansion forever. More and more we just keep expanding, or maybe even this crazy idea of this anti-gravity. Now, this is a great way to think about things, but this is not exactly what we observe. Instead, what we observe, instead of time, we measure distance. So time and distance are linked together, because as you look at things that are further and further away, they are inherently going to be from a long time ago, because it takes time for the photons to travel that distance and reach us. So we can do this by looking at very distant objects. So if you go up in distance on this plot, and then measure the redshift. So if you're measuring redshifts, that's the expansion of the universe. As a function of the distance, if you measure those things, you can determine the difference between these different scenarios. And I've got some equations on here to kind of tell you how to do this. So how do we as astronomers do this? Well, we use a kind of explosion in the sky that's not the Big Bang. We use type 1a supernovae. You don't need to know much about them. They are exploding stars, though, exploding white dwarfs, in fact. So white dwarfs are essentially, the cooling embers of the cores of a normal star like our sun. If they happen to get pushed around a bit, if they have enough material around, then they'll eventually explode. And when they do this, they're extremely luminous. They can be as luminous as some galaxies, which means that we can see them very, very far away. Now, here are some pictures of galaxies with supernovae. You can see the supernovae. They're kind of just hanging out in the galaxies often. So like here is a supernova, here's a supernova, here's a galaxy with 2 supernovae in the same galaxy at the same time. Now you'll notice it's a little bit hard sometimes to figure out what's a supernova here, or like this point over here, this is actually a star in the Milky Way. It's much closer than all the stars in this galaxy, but it just happens to be in front of it. So how do we know, if this is a supernova and this is just a star in the Milky Way? But we use very advanced algorithms to determine exactly what's what. And really what we end up doing, what seems to be the best, is to look for the arrow and see where it's pointed. Okay, so we don't exactly do that. What we instead do is we look for changes in light over time. So the supernovae, they only last for a few weeks or a few months. And so what we can do is if we make a movie of the sky, we look for the things that change. And those are often the supernovae. So here are just a few images with the Hubble Space Telescope taken before supernova and then with the supernova. And you can see our algorithm still works because there are still some very nice arrows pointing things out. Now, the nice thing about type 1a supernovae is that they have very similar brightnesses. And so from that, we can determine the distance, much in the same way if you are a Santa Cruz native, if you've ever driven down Highway 17, especially when it's foggy, you can see something like this and say, all right, I know roughly how bright a car's headlights are. And by looking at how bright they appear to me, I can roughly figure out how far away the cars are. So I can say that the brighter cars, the brighter headlights are closer, and the dimmer ones are further away. And we do the same thing with these supernovae, with one little caveat. So it turns out that they're not perfectly standard in the same way that you might have a 40-watt light bulb and a 60-watt light bulb. And we need to figure out what the wattage is on these things. Now, the cute thing about this is that the brighter supernovae in general, they decay slower. Well, sorry, 1 second. And through that decay, we can measure how slowly they decay, and from that infer how bright they are. That's a small correction, but it really helps with the work. So when we make all those corrections, we can then finally make a Hubble diagram, this distance versus redshift. So on the left here is distance in weird units, and on the right is a redshift, the velocity, and again, weird units. And what you can see is if you just treated them as if they were all the same luminosity, you'd get the right answer. You get this expansion that as you go further away, things are moving away from us faster. But if you make these corrections, then the relationship just becomes tighter and you can make a better measurement. So we do that. And back in the 90s, there were two main teams that were trying to make this measurement, try to figure out how much matter was in the universe, how the universe was decelerating. The High-Z team and the Supernova Cosmology Project. The High-Z team was led by Brian Schmidt here on the left, and the Perlmutter on the right. And these were friendly competitions, as you can see here, that both these teams were trying to do the same thing, but when they were in the same room, even though they might have been competing for telescope time or something like that, they were still very friendly. And in the late 90s, in 98 and in 99, the two teams put out their first confirmation of what they thought the universe was really, really like. And the interesting thing here is when you make this Hubble diagram, again, distance versus, in this case, redshift, and you look at it in detail, the supernovae that are very far away, they seem too dim. So dim that it meant that you had to have this cosmic anti-gravity. And so this is another way to look at this. It's a little, essentially here on the left is plotted the amount of this anti-gravity, and on the bottom here is the amount of matter in the universe. And these contours are telling us, what we think the universe is made out of. And what you really want to pay attention to is this line here. So everything below this line is a universe that is decelerating. And everything above this line is a universe that's somehow accelerating, where there's this cosmic anti-gravity. And the data were showing that the bullseye is up in this accelerating region on both of these teams, which, both of the teams were working independently, getting independent data, and both saw the same thing. This is really incredible. Back in 1998, this was, one of the headlines astronomers see a cosmic anti-gravity force at work. And then Brian Schmidt, the PI, the leader of one of these teams, the High Z team, he said, my own reaction is somewhere between amazement and horror. And what he's really saying there is the amazement is that this is truly unexpected, incredibly interesting new science. The horror is, maybe you made a mistake. Now, it turns out, decades later now, no mistake was made. In fact, the constraints have become so tight that we really know what's going on. And in 2011, Brian Schmidt, Saul Perlmutter, and Adam Rees, who did the main analysis of that first paper for the High Z team, won the Nobel Prize in physics. And just to show you, this is the High Z team at the Nobel ceremony with Adam and Brian with their medals. And I just wanted to highlight a few people here. So these are the UC affiliated people here. So Alex Filipinko, who we already talked about, professor at Berkeley. Adam Rees was a postdoc at Berkeley when he did the analysis. And then Saurabh Jha became a Miller Fellow a few years later. So just really great. And of course, this is sort of my academic family. So it's nice to see. So what did we learn? Well, it turns out that this dark energy, it takes up about 70% of the universe. The majority of the universe is dark energy, this stuff that's making the universe accelerate. It's just totally crazy. It's the majority of what's out in the universe, and we barely know anything about it. And we didn't even know it existed until 1998, when I was still in high school. So it's one of those things, like within our lifetimes, we discovered the majority of the universe. It's incredible. We are really on the frontier here. Now, since 1998, where there were just dozens of supernovae being used, we've made a lot of progress. Now there's a Hubble diagram with more than 1,000 supernovae, and we can say very definitively that exactly what's happening with the universe, where there was this period of galaxy formation where the expansion was kind of going in this slower deceleration mode because you're mostly having matter at that point. But then eventually this dark energy takes over and we get this accelerated expansion, which can continue for a while. Now, this image, maybe some of you have already seen. It's a very nice way to look at it, but it distorts the picture a little bit because it's not in time. And I was able to find this very nice picture that kind of shows it more in time, which shows that the acceleration in terms of time has been happening now for a good fraction of the universe. Now, this gets all the way back to Einstein in that, here at the top, I have Einstein's field equations. This is what general relativity is. And you don't need to know the math, but if you remember back to calculus, if you happen to take calculus, when you integrated something, there was always this constant that was left behind where you didn't really know what it was and you often forgot about it. And you're like, you got marked down by a point because you forgot the plus C. And Einstein, he didn't forget about the constant. He put it in right here. It's this lambda term. It's a constant of integration. And originally he had it in his field equations, this general relativity equation, to make it so that the universe was not expanding. And then when Hubble found out that the universe was expanding, he said, oh, well, that was a huge mistake. Why did I even include it? I should have never done that. And so for decades, they just removed this entire term and just took these first two, which tell you about the expansion. Now, this is often called Einstein's biggest blunder, but it turns out that he might be right because this term might be what's causing that accelerated expansion. It's called the cosmological constant, and it's one idea for what dark energy is. Now, the problem with this, when we are talking about dark energy, there are a few problems with the cosmological constant. So one is if you take just simple theory, if you take the simple theory of string theory, right? Very simple. And you measure what you think the cosmological constant should be. And it's something like 120 orders of magnitude, 10 to the 120, larger than what we measure. So that's about as wrong as you can get. So we are way, way off in terms of what the expectations are. Another interesting question is the universe doesn't like coincidences in much the same way that we are not the center of the universe. Why is there this coincidence that there's roughly as much dark energy as dark matter today? That seems weird. And it wasn't that way billions of years ago, and it won't be that way billions of years from now. Billions of years ago, dark matter dominated, and billions of years from now, if it's a cosmological constant, that constant will dominate. And also, we already knew about this period of accelerated expansion early in the universe that eventually went away, and that's called inflation. So it's a funny thing that we need to figure out. Open question. If you figure it out, you've just won a Nobel Prize. Congratulations. Now, getting back to this expansion rate, this what we call the Hubble constant, this has always been a hard problem. Going back to Hubble, so Hubble's original measurement is up here, where his measurement was something like 600 and something. And over time, those measurements have come down and kind of settled into this area way down here. But those measurements were kind of just all over the place for decades. And even recently, things have been kind of muddled. And in fact, one of the interesting things that has happened very recently is that you can measure the Hubble constant in two ways. The classic way, very similar to what Hubble did, by measuring the distance to nearby galaxies and connecting up the expansion rate that way, is inconsistent with what we are able to infer by looking at the cosmic microwave background, sort of the echo of the Big Bang, and then using our theory of general relativity to determine what that rate should be today. And if you do that latter, if you take the cosmic microwave background and infer what the number is, it's kind of low, like 67. And then if you do it the normal way, by looking at things nearby, it's more like 74. And that seems like it's not that much. But the difference in terms of the age of the universe, which directly depends on this number, that's really the way to think about it. If you're like, well, who cares about what this number is? It really tells you about what the age of the universe is. And if it turns out to be the lower value, it's something about 14 billion years. And if it's the higher number, it might be more like 13 billion years. Now, what's a billion years between friends? Right? And it's never very tactful to ask the universe how old it is. But at the same time, this is an incredibly important question and really fundamental to our understanding. And if we wanted to make these two numbers come together, there are, maybe we made mistakes. Like this is the horror, the potential horror that somebody made a mistake. But there are ways to bring these two numbers together by adding new physics in the same way that we added dark energy a couple of decades ago. So we could have dynamical dark energy that's changing over time. We could have an additional relativistic species, much like the neutrino. We could have some curvature to the universe. There's a lot of really interesting stuff here. And again, if you figure this out and you're like, all right, it turns out that there's a new neutrino, you just won the Nobel Prize again. Congratulations. Okay, so what are we doing about this today? Lots of problems here. Let's solve them. One of the nice things is that we are currently in the golden age of transient astronomy, these things like supernovae that change over timescales of weeks to months. What we see here is just how many supernovae have been discovered over time. And this goes all the way back to 1885, but you just can't see it on this plot because it's exploded in the last few years. If I make this a logarithmic plot, so here at the top is 10,000 and then 1,000, 100, 10 going on down, you can see that we've just been increasing exponentially over the last few years in the number of discoveries. And so what this means is it's really the perfect time to be studying supernovae exploding stars. And we can take advantage of this in new ways that just weren't accessible even a few years ago. So one of the ways that we've been doing that here at UC Santa Cruz is we've been running a couple of supernova surveys, one called the Foundation Supernova Survey, which uses the Pan-STARRS telescope on Haleakala in Maui. And then another one using the SWOPE telescope, which is at Las Campanas Observatory in Chile. Both are relatively small telescopes, but they're extremely good at this science. This SWOPE telescope, by the way, is also the telescope we use to detect that first light from a gravitational wave source. So it's always near and dear to my heart. Now, together, these two surveys, this is still work in progress, work being done by primarily a grad student, Cesar Rojas Bravo, here at UC Santa Cruz. And we already, from these two surveys, almost have as many supernovae for our Hubble diagram as that 1,000 supernova diagram that I showed that took 20 years to build up. In just a few years, we've been able to do almost exactly the same thing, and including critically, all these things here, these are the objects that we can use to measure that Hubble constant. Now, we aren't ever satisfied with the status quo, and things are really improving quickly. So we are also running this new young supernova experiment, again with the Pan-STARRS telescope, but now we're supercharging it, where we're going to observe something like 15,000 supernovae. 1,000 is not enough. And so in the next few years, we're going to make so many discoveries of supernovae. Eventually, pretty quickly, the bottleneck becomes spectroscopy, where we need to figure out what kind of supernova it is and then critically measure those redshifts. And so again, at UC Santa Cruz and at Lick Observatory, we're trying to solve this problem by building a new instrument for the APF telescope, which is pictured here on the left. This is at Lick. Maybe you recognize the great refractor down here. And this is an incredible telescope because it's completely robotic. And so this new instrument that we're building will also be fully robotic, no humans involved. And that will be really nice for the graduate students who don't have to stay up all night. One last, really important thing that I think is worth mentioning is that in roughly 5 years, we're going to launch a new space telescope called the Nancy Grace Roman Space Telescope, named after Nancy Grace Roman, who is colloquially called the mother of Hubble. She was the NASA administrator. She's also an astronomer, but she was working at NASA when she pushed ahead the Hubble concept and made sure that launched to all the glory that it has made recently. She's a fantastic choice for naming this telescope. This telescope is more or less similar to Hubble in the sense that it has the same size mirror and that sort of thing, but it can see 100 times as much sky at a time. So it's like 100 Hubbles. Perfect, that they named it after her. So with that, I can just say in a few years, things are really going to be amazing. And we'll get to the bottom of both the dark energy question and this Hubble tension question. And again, I cannot thank my team enough. They're the ones really doing the work. Many days I'm just here to make sure that they get paid and are fed occasionally. And they're the ones who are pumping out the science. So, many thanks to them. And really thank you. And, either through your tax dollars or perhaps, you were one of the incredible people who gave money through the Giving Day at UC Santa Cruz. But absolutely, in one way or another, you have supported this work. So thank you very much. And I'm really happy that we can have this conversation today. But if we run out of time, you can always, just send me an email. My email address is at the bottom here. And I'm ready to take some questions. So thank you.
Thank you, Ryan. I am going to move up. There was one question that we got on our Facebook Live feed from June. She said, based on the scale factor graph of the expanding universe that you showed us earlier, won't all densities of the universe where gravity decelerates the expansion, medium, etc., eventually contract the universe with time back to the initial scale factor and not just the very dense universes?
So, all right. So give me a second to just try to find that slide. So I think this is the slide that we were talking about. And so the idea here is that, yeah, so if you go back in time, by design, all of these different universes had to start off with a scale factor of 0, that you had to have started with a hot Big Bang. That is definitely something that is by design. We know that the universe started in a hot Big Bang, so you have to do that. You could think of some other things. People used to think about this, what's called a steady state universe, where the universe was not expanding or contracting and existed for an infinite amount of time before us. We know that not to be true. So in that sense, yes, if you go back in time, everything has to has to eventually hit that scale factor where it's equivalent to a Big Bang. The question is, when was that? And that depends on the exact content of the universe, how much matter there is, how much dark energy there is. And so I hope that answered that question.
Thank you. Richard asks, there's a difference between the cosmological constant and the Hubble constant.
Oh, yes. So this is complicated. But yes, these are two different numbers, and we astronomers like saying constant a lot. So the Hubble constant is exactly, if you're looking at this this plot here, it's the slope of the line today. That's the Hubble constant, is the slope of the line today. The cosmological constant in some way determines exactly, what the curvature of this line is in the future and what it was in the past. They are related to two different things. The Hubble constant is really telling you something about the expansion. And the cosmological constant, in its simplest form, is really a mathematical construct. Is that there are these equations that go along with general relativity, and you're allowed that constant of integration. And that's what it is in the simplest mathematical form. Many people like to also ascribe it to the vacuum energy of the universe, which is a complicated sense of just saying if you had absolutely nothing in the universe, there would still be a little bit of energy around. And that little bit of energy would cause this sort of accelerated expansion.
Thank you. Andres asks, isn't Hubble's constant not constant?
Yeah, so when astronomers say Hubble constant, this is very good. These are great questions. When people say Hubble constant, what they generally mean is the time today. What's the expansion today? Now, there's a Hubble factor or something like that where it was something different at a different time, right? And so if you could measure what the expansion rate was 1 billion years ago or 10 billion years ago, that would tell you something. And that's effectively what we're doing with the supernovae when we measure their distance and redshift, is we're measuring that expansion history. So we're trying to track out the Hubble expansion as a function of time or as a function of redshift.
Brandon asks, if explosion conserves energy and information, Newton's second law, do we have any sort of analog for explosion? For example, is there a force stretching the fabric of space-time? Do we have any clues or hypothesis on if an equal but opposite equivalent relationship might exist?
Yeah, so this is a really good question. This is a tough one. So essentially, when we talk about conservation of energy, we're talking about those that inside of like a closed system, and so it's the sort of thing where yes, if you push the roller coaster up the hill, then when it comes back down, it's releasing that energy. So you're changing potential and kinetic energy. That same thing doesn't have to happen in the universe. There are some interesting questions about exactly, where did the Big Bang come from, of course, but you don't have to have the same kind of conservation of energy. It's an interesting aspect of the theory, but more to the point of what we're talking about here is we're essentially at the point where the roller coaster is already going down the hill. So how did it get to the top doesn't matter as much for what we're trying to say, but I agree that this is a super interesting question.
What is dark energy's relationship to 0-point energy? And could 0-point energy be a potential solution to our energy needs?
Yeah, okay, so it depends a little bit on what people mean when they say 0-point energy. So one way that people often say 0-point energy is this vacuum energy that I was talking about, just like empty space where there's absolutely nothing in it. There can be some energy involved in that, and this is something that just comes out of effectively quantum mechanics, or quantum field theory. You end up having this. You just have space itself has this non-zero energy. So oftentimes people talk about that as a 0-point energy. Sometimes people confuse that with absolute zero, which is like the the lowest temperature that you can have where particles don't move around. So in that sense, they're not related. Like absolute zero is not related to dark energy. In terms of the 0-point energy, people have thought about this, in terms of this vacuum energy, people have thought about how can you extract it. There are some interesting things if you want to look up like the quantum Hall effect. There are some interesting ways to potentially gain some energy from the vacuum. However, the amount of energy, at least today, is very, very little. And so there's nothing practical that can be done. So even though we would love to, I say it's anti-gravity, and you should be immediately being like, whoa, if we can harness this anti-gravity, can't we use it for spaceships or something? It turns out that there's just not that much around us, even though there's plenty in between galaxies. If you just looked at like how much dark energy was in our solar system, it'd be minuscule. And so yeah, unfortunately right now, there's no practical way to do it. But maybe somebody very smart in the future will be able to do this. And wouldn't that be fantastic? Because then I could tell my mom that I was doing something practical with my life.
Thank you. Just a quick note from Bob Kelly Thomas. He wanted to make sure that folks knew that the Lick solar eclipse expedition of 1922 was the first to unequivocally confirm the precise amount of Einstein's prediction that the sun's gravity bends starlight. He must know our former director, William Wallace Campbell, who is the director of Lick Observatory and also the University of California. His granddaughter just made a gift in his name. It was really wonderful to see that family's long legacy here at the organization. Ed asks you, Ryan, if gravity depends upon the mass of two objects, suppose one of the objects has undergone nuclear fission, or in the sun, nuclear fusion, so the mass has decreased. What happened to the attractive force from the missing mass?
Yeah, excellent question. All right, so if we go through, our name gets bonked. Okay, so if the mass is literally changing, then the gravitational force is also changing. And so this is something that, yes, right. So you can do this through different kinds of nuclear reactions, but there generally the mass that changes is very, very small. So that's actually one way that you can do it, but it's a little bit hard. A different way to do this is actually through now, all right, this is showing my one of my other passions is you can do this through these mergers of compact objects. So if you take two black holes and you merge them together, in doing that, you can release a bunch of gravitational energy. And you do that, you convert that into gravitational waves. And that is really removed from that system. And so the combined system when they work with two black holes is more massive than the resulting black hole that merged together because there's so much energy that's being pulled away. And so that's definitely true. Now, I'll point out though that even though this equation here that I have on the screen is mostly true, this is an approximation that works on Earth plenty fine, but it's not the full story for gravity. If you really want to know the full gravitational force, you need to go to Einstein's theory of general relativity, and even that we know is not perfect. That there have to be some modifications to Einstein's theory, although so far we haven't figured out a better version of that. But that is something that, again, if you can figure out the next version of general relativity, some Scandinavian people would be happy to invite you over. So yeah, these are big questions that people are asking about.
We are just nearing the 5 o'clock hour, so I wanted to take time to thank you again, Ryan, for joining us and for presenting on Living Room Lectures this week. As we are moving into August, just several of us are also taking some much needed and much deserved vacation time. So we will not have Ask an Astronomer next week or 3 weeks from now. On August, let me make sure that I got the date exactly, August 17th, Monday, August 17th. That's in 2 weeks. We're going to have a very special sort of merger of living room lecture and Ask an Astronomer. I'm asking Ryan's former teacher, Alex Filipenko. I'm stopping my video because I understand that I'm a little bit unstable. Ryan Foley's former teacher, Alex Filipenko, who we all know and love so well. We've heard a lot about his science over the years, but I don't know about you. I'm really curious about his teaching. I want to know what it's like to be the teacher in these classrooms, what made him want to teach. How do you get students as incredible as Ryan Foley coming out and teaching on the other end? He's going to do a special interview with me where I'm going to be asking him questions about his teaching, about the research that he chooses to do with students. We all know that he could work with anybody. Why does he continue to choose to work with undergraduate, grad, and postdoc students all these years later? I hope that you will join me for that. And then at the end of the month, one of our postdocs here at UC Santa Cruz, Emily Martin, will be talking to us. She is currently building an instrument up at Lick Observatory. And I think it's a perfect example of how Lick Observatory continues to be a really important test bed of our research and our science. She's building that instrument to test the science concept that will be used for an instrument that will go on to Keck Observatory and then ultimately a 30-meter telescope later. So I'm delighted to have the two of those here in August. I can't believe it, but this is already our 9th week together. Thank you so much for coming out. Tonight we hit our top number of attendees. So I just really appreciate that you keep coming back week after week and joining us. I can't wait to see you in 2 weeks. Until then, I hope that you have a lovely summer weather and enjoy our recorded videos. Good night, everyone.
Thanks, everybody.